A ball rolls on level ground without losing any of its speed to rolling friction. The ball hits an elastic boundary and bounces off, maintaining an equal speed to what it had before, but going in a direction exactly the opposite of the direction it was going before it hit the boundary. If the ball had a mass m and a velocity v and was initially going in the negative x direction, what is its change in kinetic energy and momentum due to the bounce? So the kind of thing I'm trying to describe here, I mean, I describe this in terms of a ball and an elastic boundary, but physicists often will think about like particles that can be kind of an abstract concept. But suppose there is this ball slash particle here, and it's going to hit this barrier. So it's moving to the left, and I'm saying moving to the left because the problem said that it's initially going in the negative x direction, and I think that was just the slide. I put that in the slide to remind me that this was the way I wanted to have it go. Which you might say, does that even matter? Well, in a standard coordinate system, I think it's going to make the answer a little bit easier to look at as part of the deal here. But basically, this is what it's doing. I'm going to look at this and say, hey, this is initial, right? This is the initial thing that this ball is doing. It has a mass m. It has a velocity v. I didn't give any numbers in this question. This is meant to be more of just a concepts question in terms of how we look at like change in momentum as compared to change in kinetic energy. Now it says that this wall is described as being perfectly elastic. So let me just see if I can squeeze that label in here, elastic. What that means to a physicist is that there's going to be no energy loss there. In other words, when the ball, I'm just going to draw slightly below here. Obviously, in reality, the ball would just bounce in and bounce back, but I find it easier to look at if I kind of draw below here and say, okay, I'm going to label this as the final state of the ball, and it still obviously has a mass m, and now its speed is actually still v. That's what the fact that this wall is described as elastic is what guarantees that. If no energy is lost, or maybe I should be more precise and say no mechanical energy is lost, which specifically means no kinetic energy is lost, but that also means, you can interpret that means there's no loss of speed. Now obviously, maybe obviously in reality, if you've ever tried this with like maybe one of those like really bouncy rubber balls or something like that, they usually lose a little speed with each bounce. One way is if you drop it, you can tell that that's the case because it never comes back to the same height, which is clearly evidence of some mechanical energy is being lost if you like bounce a ball like that. Again, drop it over the floor and have it bounce upward. But we're kind of in physicist imagination land here, where perfectly elastic collisions like this can happen, and there are perfectly elastic barriers that let this happen. And it turns out you can say, well, this is physicist imagination land, but some of the physics we're developing also applies later on to more microscopic kinds of systems, right? Like maybe electrons doing something where things like drag and friction forces are less a part of that reality than the reality that we generally live in. So in that sense, it's not just physicist imagination land, but for right now it is. Getting back to the question though, we're basically being asked like, okay, we're being asked for the change in kinetic energy. So I'll just say delta K, right? We're being asked for that. And then we're being asked for the change in momentum. But the key concept really in this question and the key issue is the fact that I should have maybe put a little arrow here above the P to say that momentum is a vector. And what effect is that going to have if I ask questions like this about changes, right? Well, it's maybe trivial to see. Oh, I said the word trivial. I just realized I shouldn't have done that maybe, but whatever. I think it's reasonably easy, trivial, perhaps, to see that the change in kinetic energy would have to be zero, because what I described was a perfectly elastic barrier, no loss of mechanical energy. There are no like potential energies here that we're talking about. Maybe briefly there's some elastic if it's a rubbery ball, right? And it's deforming slightly, but anyways, some kind of elastic potential energy briefly again. But between the initial and the final state, the total amount of kinetic energy is the same if the speed has not changed, right? But momentum is a little bit different, because to calculate the change in momentum, we have to account for directions. In other words, strictly speaking, change in momentum should be final momentum as a vector minus initial momentum as a vector. And I wrote, like, heat constants page, I just had a knot here, but I've decided to change subscripts just to show you that you can, right? And okay, how do you deal with this vectors? Well, if I kind of say like, hey, let's just look at this in the x direction. So I'm going to kind of act like I do when I did force problems, right? Where I look at components. And I'm saying, let's look at the x components here. In other words, if I want to find what is the change in the x component of momentum here, well, the final, I think, momentum here would be positive mv, right? And then I'd subtract the initial momentum. We might recall, right, that vector equations are like a guide, right? And maybe I don't know, maybe I'm doing too many steps here, but you know, I'm also, because I'm basically using this vector equation as a guide to this one, but I'm also plugging in mass times velocity. That's really the same for both of these, but there is a crucial difference with the initial momentum versus the final momentum, because the initial momentum is in the negative x direction. So it really would, its x component in that sense would be minus mv. And so if I'm just finding the change in the x component momentum, it really should be mv minus negative mv, which instead of being 0, right? So kinetic energy was 0 because if you take like 1/2 mv squared initial, or sorry, final, minus 1/2 mv squared initial, and do that in the correct order, right? Since initial and final speed are the same, that was trivially 0, but momentum, again, having direction changes that. So the change in momentum, it actually winds up being 2 times whatever momentum it started with, because of the way this minus minus turns into a plus. Conceptually, you can also look at it and say, hey, since direction matters, what really happened here? The amount of motion did not change. And the kinetic energy only measures the amount of motion. But the direction of motion did change. And so in that sense, like, the object was initially moving to the left, and now it's moving to the right. So if you break that change maybe into 2 steps, you could say one change would be taking that initial motion to the left, dropping it to 0, and now going from 0 to motion that is going to the right. Well, that's kind of like 2 changes. That's like twice the amount of momentum, that really as a measure of motion, that had to be the change, right? So that kind of makes sense conceptually why this 2 had to be there, why it had to be 2 times mv, and mv really reflecting the initial momentum. So let's go ahead and check that answer. You can see here as formulas, it states what we have stated.